Okay, so we'll get started here. Thank you, Maricel, for the lead into my presentation. My name is Ryan Porto. I am a technical specialist in ergonomics and virtual manufacturing at General Motors. Today, I'm going to go over how we're using virtual reality and human simulation. Little bit about my background. I mean, I've been in ergonomics for about 20 years now, the basic kind of being an ergonomist, following a new vehicle, looking at new designs, doing reactive, kind of proactive studies. But I was actually started at Ford and recruited to come over to GM. And really, my first passion was the digital human model. So, how it kind of fits with ergonomics and how we can bring in kind of all the tools that we've heard about there in traditional ergo into the digital world and do it faster, do it better, and do it maybe 5, 6 years ahead of a vehicle being designed. So, and really all of this right now, or in the past, in the last, so probably 15, 20 years, when it kind of first started to come out with different models, such as like you've seen it in Delmia or Siemens Classic Jack. We've done kind of static types analysis and all kinds of things from energy expenditure, push pull analysis. And it's been really our bread and butter as we look to kind of push things earlier and identify issues really early. So, digital human model, a little bit about the history, kind of started in around 2007 when I came along at General Motors. You can kind of see the little bit of a hot dog shaped fingers that we were using for hand clearance, and you can kind of see the digital human model, how it's evolved and got better and better as the years go on. 2012, we actually created this digital human model efficiency toolkit where we've worked with different universities to improve the inverse kinematics. And anything what we're doing, I should have mentioned before, is this is like on a desktop, so you're kind of using your mouse, you're creating the posture based on what you've seen in the plants or based on how the car may look in the future. So in 2012, we created this almost like a flow through process. It was like an overlay over top of our digital human model. In 2013, we ended up buying a XSense, the inertial suit. It wasn't quite up to par where we could get it to dynamic simulations. We're still kind of using it for static models, and I'll talk a little bit about that later on. And now we're just kind of introducing VR to our human simulation process. So, vehicle development process, it really starts with the virtual assessment early on. We go into a pre production phase, which is basically building prototype vehicles. We bring all the plants in that are getting a variety of cars. We bring the process engineers, the designers come and check if their part can be assembled. And then we get to a product launch. And at the launch, that's really we're delivering a vehicle for the assembly plant to build. The ergo focus has always been, I mean, for where the department I come from in the engineering space is way up front, kind of in that design, the design phase. We do obviously have ergonomists in each of our plant to deal with the day-to-day operations and sprain and strains that come up. Proactive ergo. So, like I said, it all happens at the using virtual assessments, and we're doing these workstation assessments using virtual simulations. And the key to that is really identifying the issues early, and that helps our manufacturing and designers kind of collaborate together to find them while the design is still fluid. My colleague Dave Delinga in the panel kind of talked about this a little bit. When we're finding the opportunity to find the changes is really early on in the design phase. So opportunity very, very high. That goes down as we get to that pre-production, the prototype, and start to ramp up. And like I said, go into the plant. And the cost for changes as we go into the plant, that gets high as well. Anybody that's released like a die or stamped sheet metal, when all that stuff is done and set in stone, it costs thousands and thousands of dollars to get those remachined and checked. So in Ergo, we're checking hole sizes, we're checking forces, we're checking hand clearance, we're checking reaches, and we're doing that as early as possible. What allows us to do that? The digital model. So we're really using static assessments. That's kind of been, we haven't really got to dynamic yet, but that's really been what we're looking at on a day to day analysis basis. So these, like I said, are perform on the desktop, and kind of like our big four is reach, hand clearance, line of sight, and strength capability. Strength capability right now is static, so it's not a true representation of like an acceleration or a forceful exertion or looking at velocities or anything like that as you wiggle on a hose. And those are just some pictures. The lower left is like a strength capability model that we use and test every part when a designer brings that to ergonomics. Dynamic assessments, kind of what we're trying to move to. These are also performed on the desktop. They have not taken off. They're very, very time consuming. This would be a full motion simulation that we've replicated to do kind of a very detailed analysis, a step by step analysis. And you can look at, when you have all this information, you can look at task duration, the process time, the force time history. We've taken force gauges and kind of looked at that acceleration or the impulse. We can do fatigue analysis, but it is very, very time intensive. This simulation here took about 8 to 12 hours, and that was an experienced human simulation engineer to do this. And it wasn't even really that refined. We started to use motion capture, and this is really what I'm going to be focusing on today is body tracking. And this increased the efficiency of our static simulations by creating posture libraries. So what we found, we went out with this new IMU suit and our ability to streamline complex postures, because like I said, with the mouse it takes hours really to get the human in perfect positions. And are we getting it right? I don't know. Try twisting the torso, and who knows if your spine should be in that perfect location, or the leg is how the legs are balanced, or is one foot in front of the other. So we took this to like our pilot plant, or kind of like our prototype plant, and we put it on a bunch of different operators and we did all of the complex postures. And yeah, we weren't sure what to do with the dynamic kind of library, or the dynamic, all of those simulations, and package them together yet. We were like, wow, look at all these static complex postures we have. And really, we've used that to kind of put them into our toolkit as starting points for 20, 40 ergonomists that work with us on a daily basis. So all the new vehicles, they're kind of using this massive library. It also does give us, on some of the difficult jobs where there are injuries, we can look at the entire posture, and you get a wide variety of all kinds of postures, motions, tasks. And we've used IMU systems and we do have a traditional optical system that we got about 10 years ago. It's more used for ergonomics research right now. That's kind of one of these static to dynamic libraries. So those are just an example of all these postures we've created. And we may label like, here's how you put in the front bumper, or the intermediate shaft, the steering column. Here's how you kind of press the interior, and it gives us a starting point to start an analysis. So now today we're adding VR to this whole process, to our ergonomics process. It's really since 2020, the Ergonomics Lab in our manufacturing space has been conducting VR sessions using the software Process Simulate. The Ergo team utilizes VR to immerse product and manufacturing engineers to immerse them and look at advanced assemblies in a 3D environment. The focus of the immersive studies, same as the static studies in Ergo, where we're looking at reachability, line of sight, accessibility, and hand clearance. And I'm going to go through a few of those today. So a couple examples. So like I said, the line height and reach evaluations on future vehicles. I have a couple examples on those. Just going through how we host virtual reviews globally to all kinds of different teams. We look at hand clearance and line of sight, and then the use of motion capture to evaluate future and current operations. Hopefully these videos should play here. So just a little bit of an overview on how we're using the tool. So I've got a bunch of videos here to kind of talk through. And in them, you'll see this subject interacting with the adjustable vehicle structure. We use that and some 3D printed assemblies. This enables us to mimic the hard points of the vehicle and simulate reach. So it's kind of like boundary awareness. You go into a vehicle plant, the operators are constantly leveraging their postures, grabbing a B pillar, is so they can kind of reach it and get in the most optimal posture as possible, so the force on their body is the lowest. And rather than create the physical mock-up from scratch, that's this kind of adjustable structure or some 3D printed parts we throw in the scene. The new vehicle can be reviewed by members of a launch team, or even the plant virtually, which saves time and reduces a lot of cost for a mock-up. So we may kind of print this entire vehicle sometimes in its entirety. Shows a couple different features that you can kind of pull out a tape measure and some of the markups and things like that that we're using. There's kind of like post-it notes that we throw up on the screen. So as we're building the vehicle, we can kind of notate what issues we're finding. Here's an example of hand clearance. So this one really is, we're not We haven't used too much of the glove, like I found a good VR glove. I'll talk about that in some upcoming slides. These are really disembodied hands, but we can scale them to the 95th percentile male. So we take this, sync it with our current toolkit and all of the specs in our joint, like with our joint partners and all of our plants, and make sure the hand is the exact right size. And we can kind of go through like a posture library and kind of iterate through it, look for a key grip, look through a pinch grip, and kind of associate that to the part. And it gives us a good representation with these floating hands in space. Right now, on the static desktop, we do this like by hand with the mouse. Line of sight. This one has really paid dividends. So, doing vision analysis. This is something where we're kind of almost guessing on the desktop, right? It's in 2D. So we do this brand new study where we haven't seen a vehicle before. In this case, my colleague here, we're getting right up close to the barrier around like the 3D printed part to see if we can install these types of tube nuts. Can we really see this assembly? And that one, like mentioned, it has paid dividends because this has shown that we've actually, on the picture on the left, is an image of the static analysis. You can kind of see the side of that brake module. You can't really see the nuts that was performed, like the tube nuts, the secures on the right side of it, um, the lower picture rather. And then on the one on the right, it shows you I can actually see them. So the one on the left was done on a static desktop, and we said, we kind of really can't see this. So now VR has enabled us to get to 100% accuracy. That's been huge. That's been driving consistency in our models, accuracy in the models. And for line of sight and things like reach to really show different engineers, we're getting to like 100% with the use of VR. Body tracking, I had mentioned, something we started about 10 years ago. Now we're finding a use for it, and I'll kind of explain how it's kind of coming into the VR technology. In this case, you really see some pretty good seamless motions. And here we're looking at bending down under kind of like the cross member to get into the engine compartment. So with that, we'll record like a bunch of those different motions, and then we can record it, and we actually can play it in this VR app. So now you can immerse yourself and actually go in with that operator. We stream the IMU data onto the what we call Jill, our 50th percentile female, and kind of go with her in the engine compartment and see what she's seeing. Now we have, gosh, maybe it could be thousands of postures we can evaluate. We can look at low back compression. We can transfer her posture, you'll see it in a second, into the 95th male. So it might be okay for her to kind of crawl and duck underneath. Let's put the posture on the 95th male and see what happens with him, and look at his shoulder width inside the car. So this is really just to get good. The best advantage I think we've seen with the IMUs is just really good walking. Like I said, the twisted, complex postures that we're able to evaluate, and then put this data into the immersive VR scenes now. Collaboration. This has been another really big advantage to starting to do VR with ergo studies during a time when working remotely has significantly increased. As we all know, we have still been able to safely collaborate with key stakeholders across designers, manufacturing, product engineers, even bringing like product specialists from our plants around the entire country, where we know, okay, you're getting this next vehicle. Can you build it in your workstation? Going through all the safety metrics and going through all of our launch metrics to really show them. And we've able to kind of virtually, we've been able to broadcast it through portals such as Teams. And there's some like VR apps that some of this software and some other ones we're looking at, where we can start to incorporate different HMDs. So if you're in some of our headquarters in India or Korea, and you have the same headset, you can jump in and also annotate and participate in a VR review. This one is just basically done through a Teams or Zoom platform, but it has been very well received and extremely beneficial. Just going through the advantages of immersive technology, the use of VR, as I said, it has been a big game changer for us, specifically in ergonomics for manufacturing. It has enhanced human simulation studies during the vehicle development process, as I mentioned earlier, really for the design of safer workstations. We're identifying a lot of other issues that we never saw before. increased collaboration between product engineering and manufacturing engineering. It's really nice to be able for an ergonomist to say, you know what, this is, you know, the biomechanics. This is the kind of we might be failing something with force or reach, and a product engineer just might not be too educated on just the entire ergonomics process or how we use the 50th female or how everything comes together. We can bring that designer into the lab and say, hey, try it. You put this thing together when, you know, they're standing inside the structure, got to reach so far. Or it could be a blind operation. As I mentioned, the big game changer is it's provided a method to accurately assess the human capability without the physical resources of plants. So, in I guess maybe years ago, when we're kind of trying to do these simulation, we can pick up the phone and say, okay, the previous model truck, how is that done at XYZ workstations? And the, you know, the plant ergonomist or maybe an engineer or maybe an industrial engineer will get back to the ergonomist or the simulation engineer at our headquarters and say they stand on a 14-inch platform. They're doing it about once, maybe twice per minute. They do it this way. They're kind of in this bent posture. We've done a risk factor checklist on them. The posture analysis yields like spine, like torso flexion of X, Y, Z. So maybe kind of take a look at it in your simulation. Well, how do you do that with EVs? We don't have the plans for electric vehicles and we're starting from scratch. We don't have that historical data. We don't have an operator building, you know, the new Hummer today. So that's really been the payoff and the big payoff for the VR piece because we're able to do the jobs at our headquarters and with our engineering teams. Lots of challenges comes with this. So maybe as you go kind of on the floor there, maybe it's something to think about as you're looking at different technologies in the expo hall. Hand holding a controller, as we started out with just kind of like the Vive controllers, is not as equivalent to holding a part, right? Feels a lot different when you're actually holding a part. And sometimes we'd almost want to put some of the real tools in the operators in the immersive subjects' hands when they're kind of going through the study, but we can't because they got to navigate through while using the controllers. There's issues with accuracy and the hand clearances and reach. What I mean by that is we're really, you know, we're using the mouse and moving every digit to the millimeter. We need to know that when we give an answer or the result of a study to a designer or product engineer, that it's got to be pretty close to exact. And we don't want to have any type of you know, offset from where you're holding the controller to where the sensor might be. So replacing controllers with gloves for a more realistic experience when grasping all types of parts. The glove technology has just not been robust enough for us. We're not getting from the ones we've trialed so far. We're not getting consistency. We're not getting accuracy in the postures. I may grab something with a pinch grip, then I grab it again 10 seconds later and it gives me a different posture. Well, that's not going to really work for us because, like I said before, we got to get this exactly right for the designer. They could, you know, that decision could hinge on quite a bit of cost. So like I said, the desktop analysis are extremely detailed. Body tracking accuracy. There's still lots of issues with the IMUs, as if people out there have used them. I don't think there's any body tracking tech vendors out here today. But if you've have some experience with IMU sensors, you know they're kind of they do have some issues with drift, especially around metal. So we haven't used them too much in our plants. And then if you go to optical, where you can kind of get to the millimeter, that is extremely time intensive, and that's really we kind of send that to universities for really the ergo research part of it in biomechanics labs. Hardware software compatibility. We've all heard about OpenXR. When we get new different products kind of come in and show us a new product, a vendor comes in, shows us a new product, we can't test them in our app to validate like the ergonomics. So that's something we're really looking forward to as a company as big as say like Siemens or Dassault. When they come in, hey, it's already working in that type of software, maybe we can give it a try. Future state, improve the accuracy of body tracking with a robust motion capture solution, enhancing that first person capability. So it's one thing to just throw a headset on, but I got to reach, I got to do the task. That's how we evaluate and kind of move forward in our business. Accurate hand locations. and retargeting to different percentiles or different size humans, meaning, okay, I do the task, I put my headset on, I did all of my ergonomics analysis. How can I retarget my hand and torso position to a 95th male or even the 50th female who we design reach for? Accurate hand locations just means, well, if I'm reaching, I want to make sure my palm center, if I'm grabbing the part, it better not be off because we're kind of setting our reach guidelines based on that posture. Ability to define body position, recognize where you are in relative to the virtual environment. That really means taking away that metal structure that you see in the scene. I want to be able to feel when I approach a hard point. I want to be able to feel when I have to duck under. I want to be able to feel the ceiling as I kind of move through the vehicle. Um, enhance haptic feedback for grasping and collision. So don't want to have to 3D print part to kind of grab them in space. I want to feel all that stuff with haptics. Maybe tactile feel for blind operation. So I kind of know when I'm getting close to something. We don't really see everything as we had mentioned before. So having the tactile feel would really help. And then, our kind of moonshot is enable tactile force for ergonomic evaluations. What if I actually can feel the console as I load it into the center of the vehicle and feel the strain on my back? We feel it for the reach when we're holding kind of like controllers just for a second, but can I add 20 pounds to you? It would almost be like a reverse exoskeleton. Future work, we're kind of doing some of the stuff. I can't talk about it a lot, but we are doing some research in the lab where in this picture, we actually have like 3 body tracking um, pieces of hardware on where we're looking at hand locations in our ergo envelope and validating them. So, okay, if I'm reaching to 20 inches away, what is the body tracking telling me in VR? Is it 20 inches? Something have been struggling a little bit with, but we are doing some research and we might be able to publish something like this next year. VR and other wearables, wanted to end on this. Something pretty cool we've been doing to go into, we're going into new kind of motor compartments, right? And you can kind of see how we use that metal structure. Talking about exoskeletons, here's one we actually put an exoskeleton on and compared the before and after. So imagine it's kind of combining all of the wearables that are out there now. We can look at posture analysis, we can look at back compression, and here we're actually seeing, would the exoskeleton interfere, or how much does it help the operator? Could we do the entire task with an exoskeleton and compare the before and after? That's all I had. Thank you.